In this video series, we will learn how to solve 5 basic types of acid-base problems: weak acid, weak base, strong base, and buffer solutions, which consist of a weak acid and its conjugate base. Please pause the video and try this problem. Now, let's discuss the problem. Here's a summary of the solution to the problem. Now let's discuss the solution step by step. Here are some YouTube controls which you may find useful while you're watching the videos. Identify what the problem is asking you for. This problem is asking us for the pH. Identify what type of acid-base problem you're dealing with. This problem is a weak acid problem. How do we know that this compound is a weak acid? Well, the problem tells us the Ka for the compound. When a problem mentions the Ka for a compound, that usually indicates that the compound is a weak acid. Write the chemical equation. For a weak acid problem, the chemical equation involves the acid reacting with water. In this reaction, this compound acts as the acid. So, in this reaction, the water acts as the base. Based on this definition, the acid loses a proton, so the compound ends up with the formula CH3COO-. Based on this definition, H2O, which acts as the base in this reaction, gains a proton, so it ends up with the formula H3O+, which is referred to as a hydronium ion. You should pause the video and memorize these definitions for acid and base. Begin an initial change end table. The first row of the table is for the initial concentrations, before the reaction takes place. The problem tells us that the initial concentration of the acid is 0.075 molar. The initial concentration of this compound is 0, because the reaction that produces this compound hasn't taken place yet. For a similar reason, we can say that the initial concentration of the hydronium is 0. It's not necessary to make any entries in the table for the concentration of the water. The second row of the table is for the changes in the concentrations that occur while the reaction is taking place. Does this reaction go to completion or to equilibrium? Well, because we're dealing with a weak acid, this reaction will go to equilibrium, not to completion. We don't know yet how much of the acid will react in equilibrium, so we represent the unknown change in the concentration of the acid as X. If we use up X concentration of the starting material, we will produce X amount of each product. The reason that all the concentrations change by the same amount for this particular reaction is that all the stoichiometric coefficients in the chemical equation for this reaction are the same. The last row of the table is for the equilibrium concentrations. 0.075 minus X equals 0.075 minus X, and 0 plus X equals X. Now we need to write down a mathematical equation to describe the equilibrium. The general equation for describing chemical equilibrium is Q equals K. Q represents the reaction quotient. K represents the equilibrium constant. Now we can write a more specific version of the equation that's relevant for this reaction. In the reaction quotient, the concentrations of the products go on the top of the fraction, and the concentrations of the starting materials go on the bottom of the fraction. Because the water is in liquid phase, the concentration of the water is not included in the reaction quotient. All the exponents in this particular reaction quotient are 1, because all these stoichiometric coefficients in this particular chemical reaction are 1. The equilibrium constant for the reaction between an acid and water is the Ka of the acid. Now we plug specifics into this equation. From the last row of our table, we know that the equilibrium concentration of CH3COO- is X. The equilibrium concentration of H3O+ is also X. And the equilibrium concentration of the acid is 0.075 minus X. The problem told us that the Ka for the acid is 1.8 times 10 to the negative 5. Now, remember that this is a weak acid. That means that only a small fraction of the acid will react with the water. That means that X is likely to be much smaller than 0.075 molar. That means that it may be reasonable to approximate 0.075 minus X as 0.075. So in this fraction, let's replace 0.075 minus X with 0.075. Now we can solve this equation for X. Our result is that X is approximately 0.001162 molar. Now we're ready to calculate the pH. The pH is defined as the negative log of the hydronium concentration. Our table tells us that in equilibrium, the hydronium concentration will equal X. We've determined that X equals 0.001162 molar. We can use our calculator to determine that the negative log of 0.001162 is 2.93. So our answer to the problem is that the pH is 2.93. Now, let's ask whether our results make sense. Is this result for the pH reasonable? Since we're dealing with an acid, we expect to end up with an acidic solution. You should know that in an acidic solution, the pH will be less than 7. Our result for the pH is indeed less than 7. So our result for the pH is reasonable. If our result for the pH had turned out to be greater than 7, then we would know that we had made a mistake. Now, remember that we assumed that X would be much less than 0.075 molar. Is that assumption consistent with our result for X? Yes, 0.001 is indeed much less than 0.075. In fact, we can calculate that 0.001 is only 1.5% of 0.075. This type of approximation is usually considered reasonable when the percentage change is less than 5%. Remember that there are 5 basic types of problems involving acids and bases. This problem can be classified as a weak acid problem. So in this video, we learned how to solve a weak acid problem. In the next video, we'll learn how to deal with another type of problem from this list. I offered tutoring in general chemistry, organic chemistry, biochemistry, physics, math, and statistics. For more information, go to my website. There's a link to my website in the video description box.